Welcome to my GECCO poster presentation for Sparsity-based Evolutionary Multi-objective Feature Selection for multi-label classification. My name is Kaan Demir, and this work was done under the supervision of Bach, Nguyen, Mengjie, and Mengjie Zhang at the School of Engineering and Computer Science at Victoria University of Wellington. Many real-world instances of data are associated to multiple class labels simultaneously, as opposed to single label classification where each instance is associated to a single class label. Multi-label classification is much harder than single label classification. This is primarily due to the fact that there are feature-to-feature correlations, feature-to-label correlations, and also label-to-label correlations. Real-world data often needs feature selection to find the smallest feature subset that maximally increases the classification performance. However, these two objectives are often in conflict with one another, which makes feature selection a multi-objective optimization problem. The large search space of 2 to the n minus 1 feasible feature subsets require a global search technique, such as evolutionary multi-objective optimization, to find optimal feature subsets with the best trade-offs between the selected number of features and the classification performance. Sparsity-based feature selection, which is an embedded method that jointly performs feature selection and learns a matrix-based regularized classifier, has demonstrated ability to efficiently and effectively perform feature selection, but is limited by its tendency to converge at local optima and also its inability to find the optimal number of selected features. Many of the existing EMO for multi-label feature selection utilize a wrapped multi-label classifier to calculate the quality of feature subsets, which is very computationally expensive. This paper proposes a novel sparsity-based feature selection algorithm based on multi-objective evolutionary algorithm with decomposition, which is expected to efficiently evolve a diverse set of feature subsets with high classification performance. A new reference point-based decomposition strategy for MOEA is proposed to automatically select the optimal number of features in sparsity-based feature selection. In order to perform sparsity-based feature selection, we propose a new representation for MOEA. Solutions in the proposed method are represented by a matrix containing feature-to-label correlations. Here, each row represents the importance of the ith feature to q total different labels. In addition, the importance indicates how useful the given feature is at classifying each of the class labels simultaneously. Given the matrix-based representation, we can perform sparsity-based feature selection by introducing new sparsity-based objective functions. The first is the reconstruction error, where X is the training data matrix, Y is the training label matrix. The second objective function has the reconstruction error in addition to the sparsity penalization on the solution matrix. In order to automatically determine the optimal number of selected features, a novel decomposition method is proposed that decomposes the problem while using n reference points, where n is the population size. A reference point lies on the F-ratio axis, which represents an ideal feature subset with a classification error of 0, given the corresponding feature ratio. We conduct experiments of the two proposed methods using the R1 objective function and the R2 objective function across 8 different multi-label datasets. A wrapper-based multi-label feature selection algorithm using MOEA is proposed as a benchmark based on previous work. In total, each algorithm on each dataset is run over 30 independent trials. In the table below, we can see aggregate wins, draws, and losses of each of the methods in comparison to all other methods on all datasets, in terms of the hypervolume and the inverted generalization distance. The main contributions of this paper included a new matrix representation that allows MOEA to perform sparsity-based feature selection, a new decomposition strategy that can control the number of selected features with a reference point-based strategy, 2 new multi-label sparsity objective functions for MOEA, R1Z and R2Z are also proposed. The experimental results show a significant improvement in performance in comparison with the wrapper-based multi-objective feature selection algorithm.